So, what if you could play out the future? I mean, really test a million different scenarios for your business, your city, or heck, even an ecosystem, all without any real-world consequences? Well, that's the incredible power of systems simulation. And today, we're going to dive into how it helps us understand a world that, let's be honest, constantly defies our expectations.
Okay, picture this. It's Black Friday. Your e-commerce site is humming along just fine, until, suddenly, it's not. In the span of just 10 minutes, your traffic quintuples. It goes up 5x. Now, what do you think happens? Our gut, our intuition tells us, things might get a little laggy, a little slow. But in complex systems, the reality isn't a gentle slowdown. It's often a sudden, catastrophic collapse.
Because what we actually see, and what this chart shows so clearly, is not some simple slowdown. It's a total failure. A request rate that goes up 5 times can cause latency, that's the wait time for your users, to explode by 100 times or even more. The system doesn't just bend, it completely breaks.
And this all leads to a really fundamental question, right? If these systems are built by us, with rules we think we understand, why are we so consistently blindsided by their behavior? Why does our intuition so often lead us completely astray?
Well, the answer comes down to something called emergent patterns. It's this fascinating idea that a whole bunch of simple things, all following very simple rules, can create breathtakingly complex behavior. The whole system starts to act in a way you would never, ever predict just by looking at the individual pieces.
This slide right here shows a famous model by Thomas Schelling that just illustrates this perfectly. Okay, so on the left, you've got 2 groups, all mixed together randomly. Now, the rule for each individual is really simple. They only want to move if less than 60% of their neighbors are like them. It's a pretty mild preference, right? Nobody is demanding total segregation. But look at the result on the right. That is the emergent pattern, a massive, large-scale outcome that not a single person wanted or planned for.
And this is why our gut feelings fail us. Our brains, they just aren't wired to naturally compute feedback loops, or the subtle dance of thousands of interacting agents, or the profound impact of pure randomness. We look for simple, linear causes, but the world is almost never that simple.
So, if our gut is unreliable, what's the alternative? Well, we need a kind of digital laboratory, a safe space where we can run experiments, push these systems to their breaking point, and learn from what happens, all without any risk. That laboratory, my friends, is simulation.
And let's be really clear here. Simulation isn't just about making a cool graphic. It's about building a digital twin of a real system, a twin that follows the exact same rules. This lets us hit play 1,000 times over, constantly asking what if, without ever touching the real world.
You know, think about how we study any system. We could experiment on the real thing, but that's often super expensive or dangerous or just impossible. Or we could try to solve it with pure math. But for most interesting problems, the equations become impossibly complex. Simulation is the third way. It's this perfect bridge, giving us the power of experimentation without the constraints of pure math.
Okay, that's the theory. Theory is great, but how do we actually do this? How do we take a real-world problem and translate it into a working simulation? Well, let's roll up our sleeves and build one.
We're going to start with a classic, the bank queue. It's really just a simpler version of our Black Friday website crash, right? They're both queuing systems, defined by arrivals, waits, and service times. And just like with the website, a simple question like, hey, is it actually worth hiring another teller, is surprisingly hard to answer correctly with just your intuition.
Now, a logical first step is to just map this all out in a spreadsheet. As you can see, every single event is perfectly predictable. We know the arrival times, the service times, everything is fixed. This is great for understanding the basic flow, but it's a fantasy. The real world is messy. It's unpredictable.
And trying to track all these moving parts by hand, it's a total nightmare. That's exactly why we use specialized tools like SymPy. You can think of it as an automated director for our simulation. It handles all the tedious bookkeeping, the clock, the event list, so we can focus on defining the rules of our system, not the boring mechanics.
And now we get to the heart of the matter. The real, true power of simulation is unlocked the moment we stop pretending the world is predictable and instead embrace randomness.
Because the second you introduce randomness, what's technically called a stochastic process, those simple averages you love become a trap. They can hide the very thing that is actually driving the entire system's behavior. Let me show you exactly what I mean. All right, check this out. Let's look at 3 different scenarios for our bank teller service times. Now, in every single one of these, the average service time is exactly 4 minutes. The only thing that changes is the variability.
how spread out those times are. Deterministic means it's always exactly 4 minutes. Exponential means there's a ton of variability. And log normal is somewhere in the middle.
And here it is, the big reveal. Even though the average time to help a customer is identical in all 3 cases, look at what happens to the average customer wait time. It's completely different. With 0 variability, the wait is tiny, but with high variability, it absolutely explodes. This is the critical insight. Variation, not the average, is what truly drives the queue. A spreadsheet will never ever tell you this.
So, armed with this powerful new understanding, we can finally build a proper, randomized model. Let's take this insight back to our bank and use it to answer our original question in a way that actually reflects reality. Here we are, comparing the performance of 2 tellers versus 3. The simulation gives us these crystal clear numbers. With 3 tellers, the average wait time plummets from over 3 minutes down to just 30 seconds. But there's always a trade-off. Look at teller utilization. With 3 tellers, each one is idle more than half the time. So the business has to ask, is that massive improvement for the customer worth paying for that extra idle time?
And I just want to zero in on that improvement for a second. We increased our staff by 50%, we added 1 teller. But did the wait time improve by 50%? No. It improved by 600%, a 6-fold improvement. That is a completely nonlinear, non-intuitive result that our simulation uncovered, and this is where simulation goes from being an academic exercise to being a ridiculously powerful business tool. So, the model has given us a clear answer. Hire that 3rd teller. But this leads us to the final, and maybe the most important question of all. How do we know we can actually trust the model? Is our input data any good? Have we validated that the model's behavior actually mirrors reality? That, right there, is the art and science of simulation, and it's the bridge between having a good model and making a truly great decision.